Hello everybody, thank you first for attending this meeting. My name is Abdelhakim Darraz. I am a PhD student and I will introduce you our work on a subject dealing with rotating machine diagnosis using artificial intelligence. This subject is supervised by one industrial and three academic labs represented by Jean-Hugh, Jérôme Antoni, Antoni Larcher, Pierre Mollon and Gabriel Kirié. Let's begin by introducing you the thread that this presentation will follow. First, a contextualization to understand ins and outs that bring up this project. Then we will talk about artificial intelligence by firstly defining this concept and then introducing you some results achieved during this project. We will conclude by putting in perspective our future works, and finally, and if there is question about the project, it will be a pleasure to answer you. Mass production of quality equipment in the automotive industry requires control throughout the production line. These controls are done through monitoring and validation tools for both production and finished products. The use of signal processing method applied to acoustic and vibratory recordings aim to ensure that machines are in a good working order and though to guarantee the quality of the service provided by a company to its customers. Here are three machine sounds, the first one corresponding to a compliant machine. The second one belongs to a machine which has a gear defect, generating friction in the reducer. And the last one belongs to a machine with a badly balanced rotor. So that's how 100% of finished products, and particularly rotating machines, are tested at the end of our assembly lines by applying thresholds at the kinematic frequencies of the machine. However, and as you know, sometimes the techniques used don't reach the expected performance, which highly depend on the conditions under which measurements were taken. That's why it is strongly recommended to acquire sound and vibration signals in environments decoupled from noise and vibrations, and though which more looks like this than this. The problem is that often such decoupled structures are not compatible with industrial constraints, mainly because they involve high cost and space congestion. Moreover, the other point we're facing is from one production site to another, or I could say it even from one production bench to another in the same plant, it is not possible to apply the same default detection thresholds because of variabilities either coming from the environment or bench structures, involving the variation of the frequency response of the bench. This means that if we test the same machine in two different benches, measured noise and vibrations won't be the same. Our proposed solution is to learn a decision model by considering environment harshness. In our plants, end of assembly line test is a two-step process. The first one could be called objective test, where the diagnosis is done by extracting common signal processing features and checking if the features' values are between thresholds. As you can imagine, because we are in a non-mastered environment, the thresholds are quite open in order to avoid from overquality, which could lead to rework machines that are compliant. The second test could be called subjective test, which is done by a human expert, consisting in listening to the machine noise. The person is trying to recognize good samples, and when he listens to a sample which deviates from the ones he is used to, he considers that the sample is bad. We decided to test artificial intelligence methods because they have been successfully applied to all pattern recognition tasks, especially deep learning method, in order to build efficient decision models faithful to human experts' know-how and to expand this know-how. As you might already know, it involves the constitution of database, in our case, labeled database, of bad and compliant machines. That's why we build a little corpus of machine sounds acquired with just one microphone on a production bench. We designed or used several structures of neural networks such as recurrent and convolutional neural network. This little corpus is composed of 330 samples, such as 165 belongs to compliant machine and the other 165 belongs to non-compliant machines. We split this database such as 80% are used for training, 10% for validation, and another 10% to test the model. In order to smooth the effects of databases, we perform the learning process 10 times on randomly distributed samples into the different three populations, and we average performances. As we said, our samples are sound of machines acquired with one microphone. We decided to perform classification either directly on raw data without processing, which is concretely a wide-dimensional array per sample, or to firstly preprocess them by computing spectrogram of this noise signal, which is in this case a two-dimensional array where frequencies are represented on the y-axis and time on the x-axis. The color represents power spectral densities. For the classification task, we use several different architectures of neural networks, such as recurrent ones with different depths. Propagation in these networks is not only one such as all other networks. As you can see, there are here some loops allowing the information to flow in both directions of the network. Recurrent neural networks were mainly designed to address time series classification, where prediction to make at time t highly depend on decisions taken earlier. That is the case, for example, in automatic speech recognition. If you want to give meaning to a sentence, you need to consider previous words to predict the actual one. One disadvantage of these structures is the fact that these loops add a lot of complexity to the gradient descent algorithm by involving a vanishing gradient problem, which leads to poor learning of the first layers of a network. This was partially addressed by long short-term memory networks, which include forget gates in order to keep in memory only relevant information of the new input. We use this network to throw .wave data as input, and we did, as said earlier, 10 learning processes on 10 randomly distributed data in order to average and smooth accuracy. One learning process is what you can see here in this first picture. So after having split its sample into the 3 different populations of training, validation, and testing. At the top, you can find classification accuracy during the learning process, and at the bottom, it is related loss. How does this work? We start to learn a model on the training population. The learning phase is an optimization problem during which we try to find the best combination of weights to converge towards label of each instance in this training population. At first, weights of the model wasn't optimized to converge toward the expected output. But the more we learn a sample, the more the model is able to recognize this sample more confidently. But there is a limit. Indeed, if you overturn a model, this could lead to overfitting, consisting in achieving very high performance on the training population and lower performance on data which wasn't used for the training. That's why we use a validation population in black during the learning phase to prevent from this overfitting. This population is not learned by the model, we just use it to check that recognition performance on unknown sample keep increasing. In the table, you can find performance achieved for all 10 learning processes. We achieved with this method an average performance accuracy of 91.13% with a deviation of 4.80%, which is quite good, but not the best performance we achieved. Then we use convolutional neural network structures. They are famous because they allow to address many problems concerning computer vision by achieving very high accuracy on image recognition tasks. An advantage of this structure is the possibility to consider directly two-dimensional or three-dimensional arrays without the need to flatten data. When we flatten data, we may lose dependencies that two near pixels, for example, which are one above the other, could have. It involves to consequently apply filters to subsections spatially dependent of the input array, which is not directly raw but preprocessed data by computing spectrograms of the wave data. As previously, you can find one learning process. With these structures, we achieved our top performance of 98.68% with less deviation than earlier. This could be explained by the fact that spectrograms provide information in the time and the frequency domain. Another observation is that we achieved better performances in a faster computation time. In order to complete a kind of benchmark, we decided to use .wave raw data as input of a one-dimensional CNN and spectrograms as input of a two-dimensional RNN. By doing this, we just achieved 81% with the one-dimensional CNN, and we improved performance achieved with the RNN to 94%, confirming that spectrograms is a better input than raw time signal. But this remained lower than the results we achieved with two-dimensional CNN. As a result synthesis, with all networks, we achieved good recognition performances. When we considered raw time signal as input, RNN achieved better performances. Whereas, when we consider the spectrogram as input, CNN achieved better performance. Either with RNN or CNN, better results were achieved considering spectrograms as input. The top performance is achieved by CNN coupled with spectrogram as input. We have higher accuracy with less deviation on the result, which means that models are more reliable. We achieved here better classification result than the one achieved in a previous study based on feature engineering. To finish and as further works, we want to go deeper on the validation process of the built models by testing on high amount of sample and by analyzing features extracted by the deep neural networks before launching the industrialization of the proposed method. We want to address also the multi-label classification in order to be able to not only recognize bad from good machine, but also to recognize different defects in the bad class. One way to improve our results will be studied. We want to provide other physics to our model, such as rotation speed, current or voltage, in order to fully describe machine behavior with different physical point of view. And that's all for me. Thank you for attending this meeting, and if you have questions, it will be a pleasure to answer you.